us to find the Maclaurin series of this. So it's probably easier to find the Maclaurin series of this and then integrate term by term once you have that series. So we have a Taylor series. Maclaurin series is just a Taylor series centered at 0, but that's going to be probably too much work. You want to go with your known Maclaurin series. If you have e to the x like we do, this is the Maclaurin series representation, except instead of x, we have negative t to the 6. So when I write this representation, that's going to be sum from n equals 0 to infinity, just like it says. 1 over n, that's the same. Now x is different. Our x is negative t to the 6 all to the n. Okay, let's write out what each term is. If you plug in 0 in here, you're going to get 1, and then this is going to be 1. If you plug in 2 into your, 1 into your series, then you're going to get 1 times negative t to the 6. If you plug in n equals 2, you're going to get out 1 over 2. That's now positive t to the 12, because powers on top of powers multiply. If you plug in 3, you get 1 over 6, and then that's negative t to the 18th, and hopefully that's enough. We wanted the integral of each of these terms, so to find the integral from 0 to x of e to the negative t to the 6, then you just want to integrate each term from 0 to x. So the integral here from 0 to x with respect to x is just x, and the integral here, with respect to t, I should be saying. Integral here with respect to t, so that's negative t to the 6. So that's going to be now negative 1 over, that's 1 over 7 t to the 7th. Because when you take a derivative, it turns back in to that. And then this is 1 over 2 times 13 t to the 13th. Let me double check that. And then here this is 6 times 19 when I take an antiderivative. That's a negative t to the 19th. Let's see if we have enough for a pattern to make the series. This is our series. We just need summation notation. Oh, sorry, these should all be x's because we're integrating from 0 to x. So this should be an x, this should be an x, that should be an x. Let's see. Power of x goes up by 6, goes up by 6, goes up by 6. So I'm going to say x, that's the sum. Let's say n equals 1 to infinity, and if it started at 0, let me pause and see if the software wants you to start at 0 or 1. It wants us to start at 0, so we're going to sum from n equals 0 to infinity. So this first term, I need to have a power of 1. I'm going to do x to the 6n plus 1, because I'm going up by 6 each time. So I had to put a 6 multiplying the n. And if it starts at 0, 6 times 0 is 0, 0 plus 1 makes 1. Now I need to, we need to compensate for the fact that it's alternating, so I'm going to put in a negative 1. And to the n power will be fine, because when n equals 0, the first term is 1. When n equals 1, it's negative, just like it's supposed to. And then when n equals 1, we're supposed to have a 7 on the bottom. We've already got x to the 7th taken care of, so we need a 7. Then we need a 13. So that looks like that's going to be 7 plus 6n. Here in the denominator, it's going to be, let me see, where you have an n factorial. I'll show you where that's coming from. The n factorial is that this is 1. This is the n in the bottom here is 1. This is a 2. This is a 6. That's the n factorial problem pattern, right? Because 3 factorial is 6. 2 factorial is 2. 1 factorial is 1. 0 factorial is 1. But these numbers now I'm looking at, trying to make sure these match up. So this is n equals 1 term. Let's do 6 each time. Oh, and trouble is this term. I'm trying to make this work. That's a 1. Just 1 plus, so 1 plus, it's going up by 6 each time, 6n, there we go. Let's test it out. At the first term, when n equals 0, you've got 1 plus 0 makes 1, and 0 factorial is 1, so we get, this whole expression works for the first term. When n equals 1, 1 plus 6 times 1 is 7, and then 1 factorial is 1, so that's 7 in the bottom like we want. And when n equals 2, should get 13. 6 times 2 is 12. 12 plus 1 is 13, so that checks out too. So there we go. We've got our series finally. Okay, so first step was e to the negative t to the 6th power. That's close enough to a known Maclaurin series where you could just plug it in. Then we expanded this term by term, and then integrated term by term to get what they were looking for. They wanted the integral of that series. So that's this down here.